Greetings and welcome once again to my new calculus channel. I'm John Gabriel, and today I'm going to be discussing propositions 11 through 22 of Euclid's Elements, Book 3. So let's begin. Now, proposition 11, 12, and 13 deal primarily with the fact that if circles are either tangent to each other or they cut one another, then the line joining their centers is always a straight line. So what that means is if you have the circles cutting as you see there, or if one of the circles is tangent, well, let's just try and make that a little smaller. Maybe put this circle in here, I think. Yeah, something like that. Yeah, so if the circle is tangent, like let's say like that, then again this line here will be a straight line. Okay, so it doesn't matter how they cut each other, and that's all that those propositions deal with. The proofs are relatively straightforward, so I'm not going to go over them. Then proposition 14 says that if you have any two straight lines in a circle, like you see this line here, which is approximately equal to this one here, can't get them exactly right, but there you go. I mean, if I put that there, well, let's see, can I? Yeah, something like that. Then they're at an equal distance from the center. Okay, so if we do that, they're at an equal distance from the center, meaning a perpendicular distance. And this is also very easy to prove, and so that's all that proposition 14 is talking about. Proposition 15 says, in a circle, a diameter is the greatest straight line, and for all the others, a straight line nearer to the center is always greater than the one further away. And of course, if you go back to proposition 14, you'll see that that's true. So if we come closer, notice that the length of this line is greater than this line. As we go away, the lengths of the lines get shorter. So that's pretty obvious, okay? And so proposition 16 says a straight line drawn at right angles to the diameter of a circle, in other words, this red line, from this end, point A, will fall outside the circle. In other words, it's tangent to the circle. And another straight line, like F, cannot be inserted into the space between this line and the circle. And also, moreover, because this is a right angle, it says that the angle of the semicircle, this angle here, is greater than any of these acute rectilinear angles. And the proof of that is also one by contradiction, but since I'm going to be doing another contradictory proof in one of these propositions, I'm not going to do this one. So proposition 17 states that a straight line that is tangent to a circle is possible from any point outside the circle. Again, this proof is straightforward, so I'm not doing it. Now, this one is an interesting one, and I'll show you the proof. It says that the angle between any tangent line to a given circle and the line intersecting it from the center is always a right angle. So in other words, if you have this tangent line here, ED, okay, then always the angle from here to the circle is 90 degrees. I mean, from the tangent line to the line drawn from the center of the circle. So again, this is one of those typical Euclidean proofs by contradiction. You assume that FG, this FG here, is another perpendicular, okay? In other words, not FC, but that there can be another one, like FG. And if we assume that, that means that FGC, this angle here, FGC, this right angle, it means that FCG is acute, right? Because if this is a right angle here, then both these angles must be acute. And thus the greater angle, FGC, this angle here that I'm pointing to, is subtended by FC, which is the greater side. But that means FC is greater than FG. But FC, we know, is equal to FB, right? And so we reach the conclusion that FB is greater than FG. the lesser FB greater than the greater FG, which is impossible. So therefore, FG cannot be perpendicular to DE, and neither is any other line that is drawn from the center to DE perpendicular. So that's a typical contradictory proof. I've done one before this one, so I think I'm going to leave it at that. Proposition 19 is unremarkable because any radius can be extended to a straight line which will pass through the circle center. Proposition 20 says the angle at the center is double that at the circumference. So this angle here is double the one at the circumference if they have the same base. But in reality, the red angle and the blue angle do not really have the same base, because if we talk about angles having the same base in a circle, we normally refer to the vertex or the apex being at the center, in which case the angles will be equal, yes? But in this case, the angles do not actually have the same base, because one is located at the center of the circle, the circle here, and the other is part of a given circle, part of this circle here, see? So if the circles are of the same radius, like that, right, then you'll see that the angle at the center is subtended on an arc, this arc, that is twice this one. So that kind of makes sense, because half of pi is approximately 1.593, whatever, okay? And so this will work regardless of where this line here is positioned. So if it's positioned there, again, the same story. If we do that, then the arc length here divided by pi will be 1.571 divided by pi, which is a half, right? Okay, so you'll all be wondering, how come that arc length is pi? Well, very simple. It's because I chose a radius of 2 units. But if I make it 1 unit, then it's pi over 2, isn't it? Okay, so that's proposition 20. Proposition 21 says, in a circle, angles in the same segment are equal to one another. And this again is unremarkable, since it follows also from the prologue I wrote. And angles at the center subtended on the same base are always equal. Okay, we will see another example in proposition 22. So now you'll see this angle here is always 96 whatever. I mean, whatever its measure is, it doesn't change because it's subtended on this red arc. Well, if we put another circle over it, like so, okay, we'll see that this angle here, okay, this red angle, stays the same regardless of where we move this point here. So we could, for example, move the point here, and again, we'll have the same little red arc. And of course, if we gave this little circle the same radius as the big circle, then we would have the red arc, okay? And so very simply, what this proposition says is that if you take the angle, this red angle that is subtended on this arc, plus the blue angle, you'll have 180 degrees. And that makes sense, right? Because if it's subtended on half of the circumference, then it will be an angle of pi over 2, won't it? So in other words, what that means is, if you put a diameter through the circle center and you take an angle in any of the semicircles, it'll be pi over 2. And so that's pretty much it. Remember again that if Euclid had written the prologue, he would have realized how important the use of circular arcs are in the proofs. They would simplify the proofs very much, and there wouldn't be such a need for these long, drawn-out proofs by contradiction. So, hope you've enjoyed this little video and that you'll join me again for another interesting video in the future. My name is John Gabriel, and this is a new calculus channel. Till next time, goodbye.